I want to talk to you a bit about snow crystal growth, that is, how to grow a snowflake. And one of the standard techniques would be using an L system or something similar. But that has its downsides, as the results look quite symmetric and a bit too geometric in my opinion. There is this one really neat technique, and it's from a paper called A Local Cellular Model for Snow Crystal Growth by a very interesting guy called Clifford A. Reiter. Google it, it's a highly recommended paper. And in this paper, Reiter has several interesting ideas. The first being that for the simulation, we're going to use a hexagonal grid, because this grid structure resembles how water molecules would arrange in ice, that is, when water forms a crystal. This is what we call the crystal lattice, and it's got this hexagonal shape. The next thing we do is we fill all these cells with a background value, and we can think of this value as water vapor, which is allowed to move freely. Think of it as moist air. And we fill all these cells except for this single center cell, which in the next step we fill with a value that is equal to or bigger than 1. And in this simulation we will regard every cell that has a value of 1 or greater as ice. So this is our starting point for our ice crystal. The second brilliant idea that Reiter has in his paper is splitting the simulation into two parts, that is, receptive and non-receptive parts. Receptive meaning all the cells that have already turned into ice, and the neighboring cells, marked in orange here. And the non-receptive cells just being the cells where no ice has formed yet, or the cells that are not directly connected to ice, where the water vapor is still allowed to move freely. So let's look at the non-receptive part first. And what we do here is we fill the receptive cells, which means the cells that are either iced or directly adjacent to them, with zeros, like so. And next we're gonna average each cell with its neighbors, using these weights here. And you can think of this procedure as basically just blurring this, as you would do when running a Gaussian blur in Photoshop, for example, over this hexagonal image. And what all of this does is, in the areas which are adjacent to receptive cells, it blurs these values a bit. The receptive cells gain a bit, and the non-receptive cells lose a bit of their values. And this is a really simple approximation of what happens when ice forms. So free water vapor flows into those icy cells and adds to the ice, while the water vapor in these cells here is reduced. On the other hand, when we look at the receptive cells, the only thing we do is, to these cells, we add a constant, in our example, 0.1. And that's it. And in the end, we merge both streams, the non-receptive and the receptive cells, by just adding them. And this is our whole simulation. So what we basically model here is, on the one hand, the diffusion of water vapor into the ice cells, and on the other hand, just a constant that adds to the growth of the ice. So let's head over to Houdini and implement this. In Houdini, the first thing I'm going to take care of is creating that hexagonal grid by dropping down a grid, diving in there, and as you can see, this is your regular quad-meshed grid. So I'm going to abuse a sop here called points from volume to generate a point cloud in a hexagonal shape. And I do that by going up here and under point configuration, I choose tetrahedral, which will yield this alternating point configuration. Then I'm just going to dial down the point separation a bit, and in order to decrease the point count a bit, let's only scale the grid to be 4 by 4, like so. So now I have my points arranged in that tetrahedral/hexagonal order. However, what I need is, for each point I need to know its neighbors, and in order to find out which are the neighbors of each given point, let's first drop down a connect adjacent pieces sub, set that to points. Let's set the maximum points to 7 and the search radius to be 0, 0, 5, 1. So if we wire this up here and highlight it, we see we now get these connecting lines between adjacent points. Now I'm going to drop down a point wrangle, wire this up, and in here I'm just going to look for the individual points neighbors. Let's write them into an array called nays, and I find the neighbors by calling the neighbors function, which finds out to which points a given point is connected, and this just takes a 0 input slot and our current point number. And let's write that out to an attribute, to a point attribute, which should be an integer array. Let's call it nays, and this equals our nays array. So let's check in the geo spreadsheet. Yeah, perfect, there we have it. So those are the neighboring, the adjacent points to each given point. And by doing this, we can find the adjacent points by just looking into this array instead of invoking a function like pcfind or nearPoint, which are computationally very expensive compared to what we're doing here. So let's drop down an add sop here and use that to delete everything but the points. Now we have our basic grid set up and we wrote the connectivity info onto the grid. Now let's initialize the grid with our background value, which was called beta in our paper that we read. So let's drop down a point wrangle again. And in here, we're going to create an attribute called val for value. And let's create a slider for that, or an input box. And let's call it beta. Click here to create the input box. And let's just set this to 0.4. Also, we need to set the point groups on those points. And let's do that by using a shortcut, by just going add group underscore, and let's call our group ice. And this should be set to 0 for the beginning. And also, let's create a group called boundary, which is the group used to select those points that are directly adjacent to ice. And let's set that to 0 as well. Let's check if that worked. Perfect. Created the groups, created the val, perfect. As you might have seen from those images in the paper, the resulting snowflakes mostly look very symmetric. To make the growth look a bit more organic, more natural, more inhomogeneous, let's add a random factor to this background value by dropping down a point wrangle again. In here, let's, to our value, add, and let's use the nRandom function, and let's fit that. Let's fit the nRandom function, which goes from 0 to 1, and let's fit that to -1 times let's copy that. So in here what we're doing is we're creating a random number which goes from 0 to 1, and then we remap this into -1 times our random amount to our random amount and add that to our value. So basically what we're doing here is we alter the incoming value by a factor of minus to plus of our randomization value. Let's create that slider here and let's set the randomness to 0.05. Let's just name those. And let's highlight this. And in our geometry spreadsheet, let's check the val, and you see it varies around the 0.4 mark. Okay, now let's initialize our seed point, so the first point that is ice, where the growth begins. Again with a point wrangle, let's call this init seed point, init seed points. And what I want to do is, I want to use a coordinate and find points close by and set those to be the starting points. Let's create a variable called number of initial points. This should be an integer value. Let's do it like that. In our case, let's start with only 1 point. Also, let's create a vector called null position, and that should be 0, 0, 0. Then let's just find points close by. Let's set the maximum distance to something really high, like so. For each of the found points, so let's just iterate through that array of found points. Let's set the point's value to 1, so the value at which it turns to ice. And also let's set the point group of that point to ice. Like so. That did not work because this needs to be a semicolon. Let's just check. Yes, we have a 1 point here. That is ice. Let's dial this up. Yeah, and now we have 3 points that are ice. Okay, that works. Next, we need to initialize our points that are in the boundary group. Let's do that in a similar fashion by just using the naze array that we saved on the points. And we only want to do this for points that are within the group ice. And for all those points that are within this ice group, let's look up their neighboring points. And iterate over them and check if they are not in the ice group, so if they haven't turned to ice yet. If a point that is next to an icy point is not yet ice, then let's set its point group to be boundary. Let's check that. We should now have 6 boundary points, which we have 1, 2, 3, 4, 5, 6. It's good. And now let's take care of the actual simulation. So let's drop down the solver here, wire this up, and let's dive into the solver. And what I like to do in a solver is first create 2 nulls, call one in and the other one out. And let's just wire this up in here, and the out will be where my output will be. And what we will do in here is, first we split our point stream into 2 groups basically, or into 2 streams. One that are the receptive points, so the points that have already been turned to ice or the boundary layer, and the non-receptive points. These are the points where water hasn't frozen yet and is still allowed to move freely. So let's take care of the non-receptive group first. That is the group where water is allowed to move freely. By dropping down a point wrangle, let's wire this up on this side here. And in here, the first thing we want to do is, as we've seen in the paper that we read, is we want to set the receptive parts, so the parts that are in the other group, we want to set those to 0 here. So let's do that by setting the value to 0. And we'd like to do that only for points that are either within the ice group or that are within the boundary group. Like so. Next, we want to do this weighted diffusion, this kind of blurring algorithm. And we would like to do this for all points. And for this, we need to get a weighting factor for the diffusion. Let's call that alpha. Let's set that to 1.0, and by using this factor, we're going to calculate our actual weight, which will be alpha divided by 12. Now let's look at the neighboring points of each individual point that we're working on. And let's calculate the center value by using the center weight. In our case, that is value equals value times 1.0 minus the weight times 6. Now, for all the adjacent points, let's iterate through them. And at their values weighted by the weight that we calculated to our current points value. So our current points value is itself plus the neighboring points attribute value times the weight. Now on the other side of the stream, the receptive points, they are receiving additional ice growth, so to say. So let's check if the points are in the ice or boundary group. Let's just add to their value the growth value called gamma. And let's just create a slider for this here. Like so, and set that to 0.0002 in our case. And in this stream, if points are not in the ice or boundary group, we just set them to 0. Okay, so now that we're done with the separate streams, let's add both together. like so. So after we've done that, let's update our ice and boundary groups. So if points have now turned to ice by acquiring a value of 1 or bigger than 1, let's update the ice group. By checking if the value is now equal or greater to 1.0. And if so, we want to set the ice group to 1 and the boundary group to 0 for now. Now, the final thing that we need to do is update the boundary group. And we do this by running only over the points that are now in the ice group and check if any adjacent points to those points are not in the ice group, and then we move them in the boundary group. So we look up the adjacent points, and then using a for each loop, we iterate through them. And for each of those points, we check if that point is not in the ice group. And then we set its point group to boundary. Like this. And that should be it. Let's wire this to the output, head outside of the solver. Let's save this, and underneath the solver, let's add a blast mode. Set it to point groups, and let's blast everything that is not ice, like this. And let's hit play. And we see a small snowflake evolving. That takes a bit of time, so maybe we will increase the solver substeps here. Let's increase those to, say, 16. Reset it, hit play again. And we now see the basic structure of a snowflake evolving here. Okay, let's first increase the usability of the solver by first creating additional user interface elements on the solver here. So let's edit the parameter interface, and we will add 4 float controls to that. And let's call this one alpha. And this should be the weighting factor. Let's hit apply there. Let's call this one the background level, that is beta. Let's call this one background level randomness. And finally, let's call this one gamma. This is the add constant. And let's set this to the values that we already set them to. So in our case, a weighting factor of 1, a background level of 0.4, background level randomness of 0.05, and the add constant is 0.0002 in our case. So let's link up all those data here. First, let's link up the background level by right-clicking on it, going to copy parameter, and go to our init background value, and in here, let's just paste the relative reference here. Let's do the same thing for the randomness. Let's copy the parameter, and up here, let's paste the relative reference. Now let's copy the weighting factor, and in the solver, in the weighting interface, let's paste the relative reference here. Now finally the add constant, let's copy that, and in the solver, let's link it up in here. So let me check if I forgot anything. No, should be good. Okay, let's save that. So now before we start playing with all those parameters, let's try turning this into an actual mesh, into an actual geometry. And I want to do this by copying a tube on those points. So let's create a tube, set that to be a polygon, have end caps, zoom out a bit, and have only 6 sides, like so. And also let's scale this a bit smaller, so the radius should be 0.06, and the height, let's set that to 0.005, like this. Also, let's cusp the normals of that tube for the visual impression, and let's drop down a copy to points here, wire up the tube in here, and the point group coming in through a solver in here. And we see we're almost there, only we need to rotate those individual tubes. So let's drop down a transform in here, and along its y-axis rotated by 30 degrees. So we are now aligned to the grid. Next, what I'd like to do is I'd like to take into account which value is actually stored on those points and use that to scale the tube that we're copying here along its y-axis. So to do that, I'm going to drop down another point wrangle after our blast here. And in here, I'm just going to create a vector called scale and set that to be 1, our value of our point, and 1 again. So we're using our value on our point here to scale those tubes along their y-axis. Not much has changed, but you might have seen a little tiny jump in here in size. So that's all that we wanted for now. Let's just save this and maybe let it run a bit. So maybe if we want to exaggerate this, we can multiply this by 2. And so we see in here we're getting slight height differences in our tube scaling. Now we have this already intricate snowflake structure. However, let's make it look a bit more organic than just those really regular tubes copied on this grid by dropping down a VDB from polygon sub. Wire this up, set the voxel size to 0.001. So we convert this incoming geometry into a VDB. Next, I'm gonna use a smooth SDF in order to just blur this resulting voxel field a bit, and I'm just going to use a Gaussian blur here. Set the voxel radius to 2 and the iterations to 1, like so. Let's highlight that, and we see by blurring the geometry we remove a bit of detail and make it look like molten ice that's been melting together. But we're also losing a bit of volume, so let's drop down a reshape SDF, set it to dilate, 1 voxel. Now we're bringing back a bit of that volume that we lost by blurring. Finally, let's convert the VDB back to a polygon, and let's crank up the adaptivity tiny bit. So we're now getting a polygon mesh out of our VDB. Finally, let's attach a normal sub to give the thing correct normals, like so. And let's drop down a final null, which we're going to call out. Wire this up in here, highlight it, and this is our snowflake solver. Now, if you're playing around with the solver, it makes sense to highlight the copy to point stop here. Let's reset this, and on our solver, let's set up some different values. For example, let's set the background level to 0.3, the randomness to 0.01, and the adding constant to 0.0035. And let's run this. So you can see a slightly different shape evolving here, more akin to a flower or a star. Let's stop this and maybe dial back on our gamma value, and also let's decrease the randomness a bit, which will yield this more dendritic look. Let's stop this, and for another extreme, let's set our background level to 0.9 and our growth value to 0.05, and let's dial down the randomness to 0. We can see now this extremely fast growing snowflake. In fact, it's growing so fast that maybe I'm gonna dial back the solver substeps to only 1. And we can see here this more plate-like snowflake growing, which nevertheless has an intricate structure to it due to the fact that we are factoring in the value that's actually stored on each individual cell in order to scale the tube that we are copying on it. This might not look as much, but if you put a glass shader on it, or an ice shader, or a water shader on the resulting geometry, you will see those structures and they will make up lots of details. So a rather versatile solver here, a rather versatile algorithm, which due to the fact that you can play with so many parameters and randomize so many parameters or even animate parameters while simulating, will yield many different interesting snowflake structures, just as they are in real life. I hope you're having fun with this. Hope you can maybe use it in some seasonal productions. And as always, we're really intrigued to see your guys' artwork. So if you create any artwork using that techniques, please just send us a link. We're always thrilled to see what you guys are doing out there. So, it's cheers and goodbye. Also, we'd like to thank all our supporters on Patreon, especially Mohammed Alabri. If you'd like to get access to special content such as premium courses, high-resolution renderings, or render setups, head over to Patreon and have a look around.